Okay.
All right. Good morning, everybody. I have to get used to saying good morning because this is a new time for me. Welcome, everyone. Thank you for coming. It's a pleasure to have here today Dr. Ahmed Tewfik from the University of Texas. Dr. Tewfik got his degrees from Cairo University, and then from his BS, that is, from Cairo University in 1982, and subsequently his MS and SCD, Science Doctorate in Electrical Engineering from MIT in 1985 and 87. He's currently the Cultural Family Region Chair of Engineering at the Department of Electrical Engineering, and he also is the chairman of that department at UT Austin. He was the E.F. Johnson Professor of Electronic Communication with the Department of EE at the University of Minnesota until 2010. He worked at Alphatech, who is now part of the BAE, the British Aerospace, and also from 1987 to 2001, he was a founder, president, and CEO of Cognicity, a startup company, and his current research are in the area of cognitive augmentation through man-machine symbols and mobile computing, medical imaging, brain computing interfaces. You name it, he's got it. Professor Tewfik is a fellow of the IEEE. He was also a distinguished lecturer of the IEEE Signal Processing Society in 97 to 99. He received the IEEE Third Millennium Award in 2000, and he was elected to the position of VP Technical Directions of the IEEE SP Society in 2009, and served on the Board of Governors of that society from 2006 to 2008. He's given a lot of plenary and keynote lectures, which of course makes him a very distinguished guest, and it's a pleasure to have him here today, and the floor is yours.
Thank you very much, Hamid, for the kind introduction. It's quite an honor to be here, and so thank you very much for the invitation. So my talk today is going to be probably a little bit different from the typical talks that you hear from electrical engineers. And I will try to focus on a project that we have with British Petroleum. We actually just finished the first phase of the project. And the whole goal of the project was to investigate this notion of man-machine symbiosis. And specifically, we as electrical and computer engineers and computer scientists are inventing a lot of technologies that are mimicking and actually a lot of what we can do as humans. And they're not just mimicking what we can do as humans. They can actually do a lot of these tasks better than the way we can do it as humans. And so one of the questions we were asking is, can we deploy technology so that the combination of man and machine is better than man alone or machine alone? And specifically in the context of deep sea drilling. So the way that the talk is structured is I will start first with a brief introduction to, at a high level, the project, what we're trying to do, and give you an example of man-machine symbiosis. And then after that, I'm going to spend a number of slides on cognitive biases. So we think that as human beings, we're rational decision makers. In fact, we're far from being rational decision makers. And I'm going to run you through some of the theories that are out there and may give you a few examples to think about, whether you are really a rational decision makers or not. And then after that, I will talk a little bit about the statistical signal processing work that we have been engaged in, and sort of the entire philosophy of how one can use much of the work that, at least some of us are familiar with, and how that can be deployed to mitigate the cognitive biases that humans have in making decisions. Okay, so the entire premise for the project with BP was, can we deploy technology that would support two things? One is increase, generally speaking, the productivity of workers. And then second, make sure that the decisions they make are safe. And again, when you mention BP, then in the back of your mind, you should keep the Macondo event, which I'll describe in a few minutes. And part of the context here is that at the time that this project started, the price of oil was very high. The shale revolution was ongoing, and it's still ongoing. And because oil and gas production was booming in the U.S., and in particular in Texas and the states around Texas, there was a shortage of workers. And so at that point, people were coming on board that did not have a lot of experience. And people were promoted very, very quickly. And as a result, you had people in various positions handling fairly sophisticated equipment that could make decisions that had a large economic impact that may not have had the same level of experience that others may have had in these positions a few years ago. And so within that context, then, the notion was, is there a way of presenting information to the different actors? And actors could be the driller. The driller is a person that sits on the rig and who controls the actual drilling of an oil well, and also controls or in charge of a team of workers. So that person is not just running a very sophisticated piece of equipment that can, if not done properly, lead to catastrophic events. But while he's doing this, he's also commanding or leading a crew that is doing multiple tasks at the same time. So you have that level of a person, and that person typically in the U.S. is someone with a high school degree. In Europe, that person typically has more of a college degree. So there is also that difference in education between the workforce that we have versus the workforce that may be in other parts of the world. But also people who are higher in the hierarchy. So the person in charge of an entire rig, or the person who may be in charge of a number of rigs and who may not be offshore, who may be onshore at a command center. And so the question is, how do you present, what information do you present to them? How do you present that information to them? Is there a way of sequencing that information? Who do you connect to whom at what point in time in order to make sure that you arrive, or that each person arrives at the best decision they could arrive at? And best here is in the sense that if we revisit their decision a day or two or three after they make the decision, or a month after they make the decision, and we have access to all of the information, then we more or less would have reached the same conclusion or reached the same decision. There are a few things that I would like to mention here. Is that the point here was not that we're going to deploy technology in such a way that we would then say, okay, there's no need for training, or we can put anybody in a driller seat and then that would work. That wasn't the point. I mean, this was sort of augmenting a lot of the business processes that were already in place or were being put in place. And furthermore, some business decisions, and I'll allude to this later on as part of an example, or drive or determine the type of decisions that we would like humans to make in certain contexts. Okay, let me say a few words about this man-machine symbiosis, and one illustration of that, which I think is pretty powerful, is a competition that occurred in 2005. And actually, Gary Kasparov wrote about it in an introduction he wrote for a chess book. Normally, when you have an online competition, or if you're teaching an online class and people are taking exams, you would like to make sure that the person taking the exam or the person participating in the competition is who she or he claims to be. So if Hamid is taking an exam, we would like to make sure that it's Hamid. Okay, that it's not me or all of us taking the exam and claiming to be just Hamid. In this particular competition, things were different. So you could participate as an individual. You could participate as a group. You could be a machine. You could be a man and a machine, or a group and a machine. And the results of the competition were fairly interesting in the sense that it confirmed that the best machine out there can actually beat the best chess player out there. Okay, so there was no surprise in that because that had been established a few years before. But what was interesting is that the group that won the competition was not a group of the best chess masters out there, and it was not the group that had the best machines out there. So there was actually another group that had chess masters and had a fairly powerful machine, but they did not win. The group that won was a group of amateurs with a good machine, but not the best machine out there. And what distinguished them was that the machine was matched to that particular group, meaning that the interface, the way that the information was being visualized or projected back to that group, or the way that that group could put information back or their insights back in the machine was optimized. So the conclusion here is, and we're going to expand that conclusion in a sense, that if you do things right, then by having man and machine work together the right way, that you can actually push the boundary of what you can accomplish. Meaning that if I do it right, I can make people perhaps more creative or more productive or better decision makers in this context. And again, there will be things in which a machine alone is good enough and there's no need for a human being. Okay, so with that as an introduction, let's take a look at how we as human beings make decisions. Now, there are various theories about this. And what I'm presenting here is a particular theory of how this is, how we make decision making. It's based on a lot of empirical studies. And essentially, it says that when we make decisions, there are two systems at work. Okay, I'm going to refer to them as two systems. They're not really two systems, in the sense that what I refer to here as system one, which is the way it's referred to in the literature, is really a collection of systems of processes that happen in our brain. But essentially, our brains are slow, and our brains consume a lot of energy. So if we have to handle situations dynamically, we really don't have the luxury of analyzing the information the way we think we analyze the information. So we have a system which essentially works as follows. When data is thrown at us, then we're going to discard 95%, 98% of the data. We're going to try to look for patterns in the data. And then using these patterns, we're going to retrieve a quick reaction that's stored in our brain. And then we're going to use that to react to the situation. So for example, when I touch a hot mug, I don't analyze the temperature and what's happening here. I'm going to pull my hand back right away. Okay? And this system works really well for us. And it's a system that we use most of the time to deal with most of the situations. And in most cases, it's perfect. And we know it's perfect because we're all surviving and we're all thriving, and that's what we use. And this is a system that exists in us as humans, but it also exists in animals. And some of these patterns and some of these reactions are reactions and patterns that we learn as we grow up. And others are reactions and patterns that we inherit. Okay, so we inherited them over a number of generations. The second system is the system that we think we use all the time, which in fact we do not use. That second system is the analytical system. This is where you present me with data, and I'm going to dissect this data. I'm going to analyze this data. And then based on this analysis, I'm going to make a decision. The problem with this system is that it's very slow. And then second, it also consumes a lot of energy. And keep in mind that our brain consumes most of the energy that we consume on a daily basis. And the fact that it consumes a lot of energy is something that you have all experienced, in the sense that all of you, if you've been involved in certain tasks that require a lot of rational thinking, and then let's say you go back home after a day in which you were doing a lot of this stuff, you might say things that you normally do not say or that you would regret saying afterwards. And the reason that this happens is because as you were thinking, you actually consumed much of the energy that you have. And so the circuits that normally come into play and which would guide you on what to say and what not to say are no longer working. And there is a way of sort of reversing this, which is if you actually drink a lot of sugar before you go home, then you probably will do fine. Okay, so let me give you an example, a few examples, just to show you that, okay, so you know this one, in fact, this works. So the system one, as I said, we make use of most of the time, and we make use in particular when we have a time crunch or we're trying to multitask. We're not good at multitasking. So this is an example of a question that's often given to audiences just to show them or just to test the system one. You're all engineers, you know your algebra, I mean, this is sort of second nature to you. But nevertheless, if I were to give you this question, and when you looked at the slides as I was talking, if you attempted to solve this problem quickly, okay, I would bet you that most of you said that one item costs $1 and the other item costs 10 cents, okay? Now, obviously, if you take a little bit of time, you know that that's not the right answer, but this is what happens when we put you under pressure. And the point is even if you're an expert and you're highly trained and you're put in the right situation, you're going to make these types of mistakes. Here is another example that's a little bit trickier. And I can tell you that I put this example in front of one of my colleagues who is our best probability professor, okay? And he made a mistake, okay? So the question is, there is a woman, we'll call her Linda, and she is single. She is outspoken and very bright. And when she was young, she was deeply concerned about issues of discrimination and social justice. And so then the question is she a bank teller, or is she a bank teller and active in the feminist movement? Okay? Most people, when they see this, will say, well, she must be a bank teller and active in the feminist movement, even though if you've taken probability theory, you know that this event is a subset of that event. So therefore, one has to be more probable than number two, right? And again, as I said, I asked this question to one of my colleagues who's an expert, and he made the mistake. Now, of course, if you tell him, think about it, then he'll come back and say no. Now, things get even more complicated. So there is an experiment that was performed several times in several locations in which you take a group of students in one room, and you ask them to form sentences with different words. And you have another control group that goes to another room and asks them to do the same thing. But the first group, the words that you give them are words that would make them think of aging. So it might be Florida, it might be, whatever, Medicare, things like that. And the other group are words that have nothing to do with this, right? And then you ask the two groups, after they're done with this exercise, to move from one room, room A, the room in which they are, to another room, room B. And the rooms are the same distance. On average, the students who are in the room where they were asked to make sentences with words that connote aging will take a longer time to go from room A to room B than the students who were asked to make sentences with, words that do not connote that, okay? So there is this phenomenon where there is the information we retrieve then guides how we behave in a completely transparent way to us. And again, this is one of the phenomena that we'll talk about later on. This anchoring phenomenon is another one that's extremely interesting and extremely pertinent to the type of problems we were dealing with. So if I ask you to add the digits in your phone number, and then I ask you, how much are you willing to bid for Hamid's car? Those of you who will end up with a large number, so you look at the digits and you add them up and you end up with a large number, will tend to bid more for Hamid's car than those of you who end up with a small number. And of course, the digits in your phone number have nothing to do with his car, right? But nevertheless, there is this anchoring that happens to us. And that anchoring phenomena has been studied in a multitude of settings. So for example, in lawsuits, lawyers who ask for large damages will tend to get larger settlements than those who start with smaller settlements. And similarly, if you apply for a job and they ask you what's your expected, what kind of salary would you expect to get, if you give a large number, okay, now it cannot be outrageous because then it'll be discarded, but if you give a large number, you will tend to end up with a larger salary. And I actually got to test this recently because we have an administrator workshop that we have to go through every year. I mean, this has been the last couple of years. But there was a training session on negotiation that I was part of. And as part of that session, we had to team up and negotiate with another person. And it so happened that I was negotiating with the dean of the business school. And so he was supposed to be making me an offer. And I used this trick on him. And I actually sort of won this negotiation, as you know, because you tally the number of points and that each of us gets. And so this is a real phenomenon, and it's an important phenomenon. Okay, now these biases come into play all the time. There are a number of factors that influence how they affect your decision and for how long they're going to affect your decision. I mean, the effect is a long-term effect. It's not just an instantaneous effect. It can take several days. And so people are aware of this. So this is why during elections, there is an art to releasing negative information about your opponent. I mean, if you release it too early, it's not going to have the same effect. If you release it too late, then it's not going to have an effect at the vote. Okay, so there is an art to doing this. And so these are some of the phenomena or some of the things that we would have to take into account as we model cognitive biases and we try to deal with these cognitive biases. Okay, let me skip this and let me move to the Macondo blowout. So a few years ago, as most of you are, I'm sure, aware, there was a disastrous explosion in the Gulf of Mexico. And as a result, lives were lost, and the damages, the economic damages that resulted were tremendous. And the question is, why did this happen? And to try to understand why that happened, there were a number of groups, and in particular, there was a federal commission that was put in place, which had representatives from the industry and various experts. And they studied what happened at Macondo over a period of time. And so you can read the entire report, and they'll show you what happened from way before the explosion happened to the point where the explosion happened. They have traces of all of the signals that were collected, all sorts of decisions that were made. And the report clearly shows that the Macondo event was a result of a sequence of bad decisions made by a number of actors, sometimes independently and sometimes as a group. And what I'm going to do is I'm going to show you, I'm going to illustrate a few of the issues that happened and try to convince you, or hopefully continue to convince you, that these cognitive biases are important and that perhaps there is a way of mitigating them. So to understand the Macondo event, we need to understand a little bit about how oil exploration happens. So what happens is when you think that there is oil in a particular location, is you bring one of, if it's offshore, you bring one of these huge rigs. And so this is a picture of part of a rig. The rig is over the rest of the image here. And a rig, you can think of it as a huge boat that will float at a particular position, will be stabilized at that position. And then we're going to use that rig to actually dig a well. And so there is what's called the riser. So there is a column that will go from the rig down into the sea, down into the earth. And we're going to dig. So we have a tool that will actually break the earth. And then we have mud flowing to remove the heat and remove the debris. And we're going to do all sorts of testing as we go through this process. And I'll allude to this as we go along. Once you find oil, then you do not want to maintain that particular rig, because that rig is huge, it's expensive, there's a large crew. So what you do is you close the well, you move that rig, and you replace it by a much smaller rig that is meant for production. Because at that point, the only thing that you want to do is just pull the oil from the ground. You don't need all of the sophistication, all of the testing that normally goes with the exploration phase. So what happened at Macondo was that BP had found oil at this particular location. They had this huge rig, and now they wanted to close the well, move the rig, and replace it by another one. The crew on the rig now knew that their task was done. This was, and they wanted to go home as fast as possible. And so there was sort of a rush in trying to do this job. Now, before you move the rig, you have to make sure that when you close the well, it is going to be closed shut. I mean, that there is not going to be a leak, that the oil that you discovered is not going to come up and then spread in the ocean. And so what you do is, what you want to do is you want to put a cement lock at the top of the well that you dug in the earth. And before you remove the rig, you want to make sure that this well will sustain the pressure coming from anything coming out of the ground. Now, once this rig moves, then what you're going to have above the well is just going to be water. While digging, what you have is a column of mud, which is much heavier than water. So the first thing that we need to do is we want to check that if we have something that's lighter than this mud, that whatever we put to close the well will sustain the pressure coming from the ground. So in order to do this, you close a particular valve, and then you displace some of the mud, and you replace it by something called a spacer fluid. And then you try to drop the pressure within the column to 0 psi, and you want to check that it will stay at 0 psi. If it stays at 0 psi, it means that there's nothing coming from beneath. If it doesn't stay at 0 psi, it means that you have a leak from outside into the well. Okay? So, and I apologize. I mean, this is one of the graphs taken from the report, and I'm not going to go through this. I mean, even me from this distance, I'm having a hard time reading what's on the slide, but that's not the point. The point is the engineers on the well performed a number of tests, including this negative pressure test, in which they bleed the pressure into the column, and they need to maintain it at 0 psi. And what happened was that the pressure did not stay at 0 psi. Now, they looked at the data and said, well, it didn't stay at 0 psi, and they came up with an esoteric explanation of why that happened. So they had some complex scientific explanation for why that happened. The head of the rig wasn't happy, and so he had them do the test again, same thing. And everybody was arguing that it's okay because we have this phenomenon. And so he insisted on running the test one more time. That time, the way they did it is they did not run the test in the main line, but they ran it into one of those secondary line, which they call a kill line. I mean, this is a line that's on the outside that allows you to inject fluid into the well. So in this case, they were able to maintain the pressure at 0 psi in the kill line. However, when they performed this test, the pressure within the main line should also have stayed at 0 psi, and it did not. Nevertheless, they said, well, we brought it to 0 psi in the kill line, so we're fine, and let's move on. So at that point, since they decided that they were going to move on, then what they were going to do is pump all of the mud which was in the column out, and then they would have to get rid of the chemicals that were in there. There was a little bit of a complication here, because normally the regulations say that all of the chemicals that come out have to be treated in a particular way. They have to be transported to shore and then cleaned in a particular way. However, there was a loop in the regulations that said that if these chemicals were part of your spacer fluid and something else was happening, then you could actually dump it overboard, and you didn't have to worry about carrying it on shore. So BP, in this particular case, because they had used a newer spacer fluid, was using that loophole, and they decided that they were going to dump the fluid off board as opposed to carrying it onshore. Now, as they were doing this, they were pumping the mud up, and they were pumping at a constant rate. And as they were doing that, and so you have the driller who's doing this action, something strange happened. And that's strange things that happened. Of course, I don't understand, although I took fluid mechanics a long time ago, but I guess a mechanical engineer would understand, is when you're supposed to be pumping at a constant rate, the pressure is supposed to be constant. And in this particular case, they were pumping at a constant rate, but the pressure was steadily increasing. And the fact that the pressure was steadily increasing, one of the reasons that the pressure could be steadily increasing was that, in fact, there was a leak and there was gas or fluid going back into the well. And nobody picked this information. Now, you have to keep in mind that today, on an oil rig, you have multiple levels of checks. So the driller is looking at this information. I'll show you a picture of the driller setup. But the driller is looking at also a lot of information. So you could say, well, the driller was distracted because he was looking at this information. He was guiding various people doing a number of things, so he missed that. But there is another crew in another room that is looking just at that information. And on top of this, the person in charge of the entire rig also has the information displayed in his office. So there were multiple independent checks. And today, this information is also transmitted onshore to a control center that sees the information from multiple wells. Yet, nobody picked this up. Then, at a later point, something more ominous even happened. So they had pumped all of the mud up to the surface, and now they were going to deal with the spacer fluid. So they stopped the pump, and as they were getting ready to shift from removing the mud to removing the spacer fluid, and even though the pump wasn't working, the pressure was continued to build up. At some point, the driller realizes that the pressure is going up. But at that point, they literally had a few minutes to live. Because a few minutes later, the fluid, the gas that had been going into the well, came to the surface. There was a major explosion, and that was it. OK, so how do we deal with this problem? Or how can we, as engineers, try to deal with a phenomenon or a list of phenomena that have been studied by psychologists mainly in an empirical settings, and where we do not have a theory of why it works or how it works. So the approach that we think that we came up with is sort of a philosophically equivalent or similar to the approach that we as engineers took years ago when we approached coding, audio coding, video coding, image coding. And so what happened then was that we took a lot of empirical evidence that came from psychoacoustics and psychovision, et cetera. So it came from the medical field and from the psychoacoustical field, et cetera. And we took that information and we mapped it into mathematical models that could help us predict whether we would hear a particular sound, we would hear a particular change in a given sound, or a particular modification in an image, or certain details or an image or a video. It did not, these models were not meant to explain how our brain works when it sees or understands the information. But they were good enough that we were able to develop the audio, image, and video coding algorithms that all of us are currently using. So not only those in signal processing, everybody's using them when you use your MP3 music or any of the videos that you're using. So the idea here is similar. We're going to take empirical information. We're going to come up with mathematical models. And then using these mathematical models, then we would engineer, I'll call them interventions, so ways of manipulating, and again, manipulating humans or the information that's presented to humans, hoping that in the end, they will make the right decisions and we can overcome some of their cognitive biases. OK. So how does this work? Well, the way that this works is as follows. You have the oil rig. There is a lot of sensor data that's being pulled from that rig. We're going to take that sensor data. Some of that sensor data is also fed into what I will refer to generically as machine learning type of algorithms, which now in the press people refer to as AI types. We might like to refer to them as statistical signal processing algorithms. These algorithms will take the data, they will manipulate the data, and they may make certain decisions. They may say, well, we think that there is a stuck pipe or we might think that you may get a kick or something may be happening in the next few minutes. In addition, we're going to monitor the human beings involved in making decisions or manipulating the various instrumentation. And we're going to monitor them as in we are going to collect the information that they're seeing, the communications they're having with others, In a future world, we may also monitor, how many hours of sleep they've had, et cetera. There may be physiological measures. And all of that is then going to go to, let's say, a big brother type of central processing unit, which then will make certain decisions and in terms of what information to display, at what type, at what point, and in what form, and how to alert the different people, whether that's the individual driller or whether it's group decisions that are being made on the rig or onshore. And if I had more time, I would have given you some of the examples of what happens in these contexts. Okay, in terms of the models that we're going to be using, our starting point was really the work by Kahneman and Tversky, which essentially defined the cognitive biases as departure from the Bayesian way of making decisions. So we're going to use that as our starting point, and we're going to take the empirical evidence, and then we're going to take that empirical evidence and say, okay, if we had a Bayesian approach for solving these problems, this is a solution. Well, the empirical evidence tells us that the humans weren't behaving this way. How do you modify the Bayesian formulation to account for these cognitive biases? And we'll go from there. There are more complex models that have been developed by psychologists that try to model the way that the brain works. They're fairly complex. And at least in our first try, we thought that those were too complex for us to be able to make real-time decisions on what to do and what to present. Okay, very quickly, how are we going to play these decisions back the information? How are we going to make our interventions? So the driller sits on a chair like this one. He has in front of him, and because I only have seen men in the driller position. So they have these two screens in front of them. These screens will display information regarding the specific task they're doing. So if they're drilling, for example, it may display the weight on the drill bit. It may display information about the depth, etc. But then on the sides, there is this very complex display that has a large number of displays. It might have displays on the output of certain spectral analysis that are being done by sensors that are down in the bore. It may have information about flow, etc. So this is a picture of the driller again. And this picture also shows another effect which I alluded to, which is that the driller is also in charge of the entire crew during that particular shift. And then further, keep in mind that the driller and the entire crew work 12-hour shifts. Okay, so at the end of those 12 hours, they're pretty tired. Okay, and they're doing whatever they're doing, but it's more in an automatic pilot mode. So the idea here is that we're not going to replace the current screens they have. So there is all of this information. I mean, there's too much information for any human to actually absorb. We will keep it in place for a number of reasons, including legal reasons, so that all of the information was there for you to see. Okay, and that's more or less what's happening. But in addition, what we're going to do is we're going to augment what they're seeing by displaying information in the right sequence that is pertinent to what they're doing now. So for those of you who may have driven cars, for example, with heads-up type of displays, you know that these heads-up displays only show you information that's pertinent to what you're doing at this point. So if you're on cruise control, they'll just show you your speed. If you're asking for directions, they normally are not going to clutter your display showing you where to go, but before you come to a point where you have to turn right or left, they will start to show you information while we're going to start to take a left and then show the distance. But normally, they're not going to show you that information. So the idea here is that you're going to show them what they need to see in the right sequence at the right time, but you're going to show them the minimum amount of information. Okay, as an example of how this might work, I'll just explain a particular task that is done often during driller. So when you're drilling, you typically drill for about 15 feet or so, and then you stop and you remove the drill bits and you have the fluid circulate, and you look at how much fluid has been going in and how much fluid is going out. The reason you do this is because you want to make sure that you did not damage the surface. And so there is no leak into the well, or there's no leak out of the well. And so you wait until you do this balance, mass balance of what came in equals what came out. That will tell you that at least over these 15 minutes, these 15 feet, nothing happened, or during that time interval, you're fine. Now, because of the distances involved, currently, the wells that are out in the Gulf of Mexico to perform any of these tests will take about 20 to 30 minutes. Okay, so if you want to make sure that, okay, I'm done, and I know I injected so much water in and so much mud, and I recovered so much, it will take you about 20 to 30 minutes. As you go to ultra-deep drilling, which is sort of what is expected to happen in 2018, whether it happens or not at these oil prices, I don't know, but you know, a few years ago, 2 years ago, this was the plan, then this might take about an hour. Now, keep in mind that running an oil rig is fairly expensive. It's a multi-million-dollar, it's a million-plus operation a day, okay? So you would like to cut down the time that it will take you to make a decision, I have a problem or I don't have a problem, while maintaining the same level of accuracy or confidence in your decision, okay? Now, the confidence level is something that the businesses have to make. I mean, it's not an engineer that will make this decision. It's the company that will need to make a decision on what it's comfortable, what kind of risk it's comfortable taking. But the idea here was that what we're going to do is, instead of measuring the amount of flow coming back and waiting until it reaches steady state, well, we would like to come up with something like a sequential detection test, in which after we get some information, we would be able to show the driller that, in fact, he can make a decision with the confidence level that's desired, and he can decide that if I waited for another 20 minutes, the test would pass, and so I don't really have to wait for those 20 minutes. Okay, so we came up with two scenarios, and these two scenarios reflect this problem and other problems. I will have to tell you that these scenarios at this point are toy scenarios, in the sense that they presume that I have access to all of the data, and I'm going to make a decision on what to show to the driller, as in I'm going to show all of the information to the driller in a particular sequence, or that I'm going to show the driller only a subset of the information. Now, I can argue that because I have access to all of the information and I was running all of these analytics, I really don't need the driller. I mean, I could make the decision instead of the driller because I can more or less predict what's going to happen. But nevertheless, this exercise was important for us for two reasons. One is it establishes that, in fact, we can predict or we can affect the way people make decisions. And second, we felt that it was a necessary step towards the full man-machine symbiosis, which we haven't solved yet, but I'll say a few words before I conclude. Okay, so in the first problem that we considered was one in which I have a lot of data, and I'm going to sequence the data to a particular person so that the person makes the right decision. Now, this looks like a normal sequential detection problem in which, instead of showing you a bunch of data and asking you, is there a fire or there's no fire, I'm going to play the information to you. And at some point, at each point, you're going to decide, I need more data, or I can make a decision, and I'll make the decision. Which, again, all of you, even those who are not in statistical signal processing, you do that all the time. Because if I call you on the phone, sometimes you recognize my voice immediately. Sometimes it takes you a little bit longer before you recognize who I am. And you might ask me to continue to talk until you recognize who I am. Okay? So that's something we do all the time. Now, the difference here is that because the decision maker is not a machine, it's a human being, then the order in which the information is going to be presented will affect the way that the person is going to make the decision. And then second, and more importantly, or related to the first point, the target probabilities or thresholds that we use that we might translate to or that may correspond to what we do in a Bayesian setting actually change because of things like the anchoring phenomena, for example. Meaning, if I present you with certain information, if you are hyper cautious, you may become less cautious, etc. So your goal and your willingness to make a decision is not something that you decide a priori. It is something that changes dynamically as I present you with data or as you interact with others. But it turns out that because your desired goals change over time, it makes the problem mathematically tractable. And so let me show you a little bit about some background on how we get to what we got to. In a very simple sequential detection test, if it's a binary hypothesis testing, when we're going to take all of the data and we'll collapse it to a single number, a statistic, and we compare with the threshold. And if it's higher than the threshold, we decide there's a fire. If it's lower, we decide there's no fire. Okay? And the way we do it, assuming that the data is independent, is something like this, and it depends on the model. But generically, this is what happens. If a human being is involved in the decision, then things are a little bit different, meaning that the way we as humans update our belief really depends on our state of mind and the kind of biases that we are experiencing at a given point. So we may give a lot of information, a lot of weight to some of the data that we receive, or we may discard it completely. So for example, if we're in the middle of August and somebody walks in my office and I'm in Austin and he says or she says it's snowing, I probably will discount this information. Okay? I mean, it will take a long time and lots of information to come in before I start to react to this, right? So there is that effect. The other effect is, as I said, the way we compute our thresholds in our mind also is dynamic and depends on the information that we have seen. So these thresholds are no longer constant. These thresholds then become, a function of what I've seen and the sequence in which I've seen it. Okay? And there are empirical studies that have been performed in the psychology literature on things like if you have analysts trying to predict stock prices, for example, how they're affected by others, how they incorporate information from others into their predictions. Okay? So we can use these models and build on these models to come up with these modifications. So for example, in our context, there are a number of biases that we looked at. There is this confirmation bias, which is if you tell me something, I will tend to believe it, and then it will take me a while to disbelieve it. Okay, so it's not the case that when you tell me something, I analyze it, and then I decide it's true or not. If you tell me something, I will believe it, and this is good for us as sort of a species because, again, it minimizes the amount of energy that we need to survive. But it's kind of a problem because I will look for information that confirms what I have heard or what I currently believe, and I will discount information that does not align with what I was told or what I currently believe. It will take some time before I get out of this frame of mind and I start to then absorb the information that I'm actually seeing. Okay? The anchoring bias I already referred to. The primacy effect is an important one in which as information comes to me, I will analyze this information, but after a while, I'll stop paying attention to the data. Okay? And so there are various ways and I thought I had changed this on my slide yesterday, but I mean, these are the WKs, not the PKs. There are various ways of modeling these to reflect these biases. And sometimes these weights will depend on both your current likelihood that in your mind and the data that you're seeing. Okay. I'll skip this because I just said it. But let me focus on this slide because it's a fairly interesting slide. It summarizes some of what we have seen in this context in which there is a lot of data, and the only thing I'm going to do is I'm going to rearrange this data, play it back to you, and see when you make a decision and how accurate your decision is. If I don't order the data, so the data comes and I'll just play it to you, and I'll play it to a machine that's running a sequential decision test, the machine will do better than you, so sorry. The blue curve is an optimal sequential detection test for this particular case, and the dotted curve is the human being. And generally speaking, the sequential test will do better in the sense that it will reach a decision faster, and its error rate will be lower, which is fine, which sort of we expect. What's interesting is if we start to manipulate the data and order it. Now, if I start to manipulate the data and order it, the distribution of the data is no longer the distribution that existed before because there is some manipulation that went on. But what's interesting is that for the human being, you start with a probability of error that looks much lower than what you can achieve with the sequential test, and with a much, you can make the decision much faster. Then after a while, then you get another curve that initially starts higher than the sequential test, and then has a behavior similar to the sequential test. So why is that? Well, what's happening here is that over time, we're able to overcome the cognitive biases, and therefore, our decision becomes as good as a machine that doesn't suffer from the cognitive bias. What's happening here is rather interesting. What's happening here is that we are, in a sense, cheating. And what is happening is, here you're dealing with individuals that are easy to manipulate. Okay, so they're not cautious. Whatever you tell them, they were going to make a decision based on that. So what is happening is the algorithm is actually looking at a ton of data. Let's say it's looking at 100 samples. It is showing you one sample that is most likely going to make you make a decision that, there is a fire. And so, in effect, you're making a decision on this one sample because you're believing, in a sense, you're parroting whatever the algorithm, whatever the machine is telling you. And so you're making a decision as if you had the 100 samples, whereas the sequential test does not have access to those 100 samples. So the behavior here is, if you are one of these individuals who believe or are easy to manipulate or who trust the machine, then you may actually do better than the sequential test. Now, the opposite is that if the machine is not a benevolent machine, it can lead you in the wrong direction. The second scenario is another interesting scenario, which was more pertinent. Yes?
Yeah, regarding this, the adaptivity, one thing I realized is very difficult to deal with humans, because humans can change a lot, and the individualized scenario depends. Also, if you take some sample to learn it, the situation may be different.
Yes.
Then it's very hard to adapt to new scenario based on old information.
Yeah, so the full picture is that the model, so I would like to have a model that is your model, not Hamid's model, not my model.
Yeah.
And your model, the way we do experiments now is we will do a run to model you, and then we'll run it. In a real scenario, obviously, this model will have to continue to change adaptively, because, as you said, it's changing all the time. It's adaptively changing with the scenario. At some point, I may be hyper cautious or less cautious or whatever, and so where my decisions are going to go is very complex. And this is a question that we haven't studied yet.
Well,
very complex question.
This is a classical question.
Yeah.
How do we know the truth?
Yeah.
Right?
So yeah.
The true model, even the same person, depend on different scenario, different stress.
Yeah, so the way we approached it in the BP context is, I'm not going to look for the true model. What I look at is that in the end, the decision that you make, if I revisit that decision in a day or two, I'm not under pressure, I am not, that I will more or less arrive at the decision that you made. In another context, similar context where with Northwestern, where this is being applied in a hedge fund, the way we're looking at it is, if you make a sell decision, then the way we're going to gauge whether this works and whether you made the right decision or not was to look at the price of the stock that you're selling 30 minutes before and 30 minutes after, and then within some bands, you made the right decision within a different band. Now, you can argue with this, it's not a ground truth, but that's a way of just approaching it, right? But yes, there's no way we're going to know exactly, and you have to adapt because it changes all the time. Because of what you're seeing, because of your physiological conditions, because of a number of things. The other problem is that we looked at is another fairly interesting problem, which is, in this particular case, I am trying to decide on a subset of data that I want to show you. And I would like to make sure that the decision that you make based on that subset of data is almost equivalent to your performance, is almost equivalent to the performance that let's say, a machine or somebody who doesn't suffer from cognitive biases will experience if they had access to the entire data, okay? And it turns out that, I'm going to skip all of these slides, turns out that this problem can be solved by modifying a well-known algorithm in theoretical computer science called the approximate subset problem. In the approximate subset problem, essentially what happens is I have a number of positive integers, and I would like to get a subset of these that comes as close as possible to a particular target. So think of the target. I have a truck that has a certain capacity. I have a number of boxes. I would like to put as many boxes on the truck, but I cannot exceed the capacity of the truck. And there is a way of solving this problem in polynomial time. If you say, I'm not particularly interested in the optimal solution, but I would like to be within, let's say, 2% of the optimal solution. So once you tell me I'm happy to be 2%, 3% from the optimal solution, then there is a way of solving the problem in polynomial time as opposed to exponential time. The expansion here was that there were two things that we needed to worry about. One is that we're dealing with beliefs, and some are positive, some are negative, so it's not only positive numbers. And second, because we wanted to minimize the number of data points presented, we had to keep track of the number of entries in the list that we're presenting. So I'm going to skip all of this stuff, and I'll show you a couple of slides since I'm almost out of time. So this is a case in which we were testing only for the anchoring bias. And there are a number of curves here, but essentially, if you do it right, then in this particular example, with about 10% of the data, you could get similar performance to if you were showing the entire data. Similarly with confirmation bias and other biases. OK, in the remaining 2 minutes or 3 minutes, let me now try to move to a question that we haven't resolved yet, which is how do I get to complete man-machine symbiosis? As I said, the problems I've looked at so far are toy problems because there was an algorithm that looked at all of the data and could make a decision based on all of this data. But what I would like to do is I would like to exploit the fact that I have man and machine. And why is that important? Well, it is important because the machine is trained on a set of data. It's a limited set of data that, whatever it saw or the person designing it saw is what they used to design that. Man, on the other hand, also has some experience. So, for example, that driller could have been on another rig in a similar situation or maybe a few miles away, and he or she may know something about what the geology or may have experienced certain problems. So in particular, as I'm presenting you with information or as we're having discussion, your brain retrieves other information that maybe confirms what I was saying or retrieves information that is pertinent to the setting. Now, if I can take that information and complement it with the information that the machine is analyzing, we may actually have a better decision because now we have a larger data set in some sense, a larger observation on which to make a decision. Now, there are two issues here, which is that initially I was presenting with you data in a particular order, hoping that you make a decision. Now what's happening is that I'm going to present you with this information. And as I'm presenting with you this information, you will decide, your brain is acting, and it may recall or not recall, or it may take time to recall the information pertinent to this situation. But that's not the end of the game, because I may be looking at Hamid, and I know Hamid pretty well. And so I recognize him, but I'm unable to retrieve his name. And believe it or not, it happens a lot to me these days. Okay, so I'm in a setting and you have to recognize someone, and you're looking at them, and you draw a blank. Okay, and even though this is a person that works with you all the time. Okay, so there is the issue of also the information is there, but I'm unable to retrieve it. But if I'm able to retrieve it, then I can concatenate it in some sense, theoretically, with the information available from the outside world and make the decision. So now the question of presenting the information to the human being is not just about undoing or mitigating the cognitive biases, but it's also retrieving other information that may help in this particular situation. So these are the models we're using. We don't have an answer yet. And obviously, this is a blind problem, meaning I don't know what you know. The machine doesn't know what you know. And in fact, you don't know what the machine knows also. You're a pilot. You have an autopilot. You don't know how it was built. And we have proof of that in some of the accidents that have happened recently. Okay, how do we, and this I think is my next to last slide, so I'm almost done. How do we test these things? Well, the way we do this testing is we actually do have a simulator, a rig simulator in our petroleum engineering department. So we can generate situations and see how people react to these situations with and without the interventions that we're doing. So I'll close by saying, I think it's an interesting problem. It's a very complex problem. It's not going to be the case that we will know what the baseline is and what's the optimal solution is, et cetera. But so far what we've done is we've tried to come up with proxies that would allow us to say, this decision was a good decision or this decision was not a good decision. The information asymmetry that I alluded to is a real problem, meaning that, again, you don't know what went into the design of the system, and the system doesn't know you or will know you over time, and it will never know you perfectly. And there's another effect, which is you get to trust the system, so you disengage completely. And that's a big problem. That's a big problem that we're seeing, again, with pilots and others. And we know that anytime you have a system that may require some of your attention but is otherwise doing everything, that we as humans disconnect. Okay? So with this, I will close by saying that I think that there is a future to man-machine symbiosis, and in fact that as we continue to develop the various algorithms that we as electrical engineers and computer scientists are developing, that's not going to put us all out of business, and we still have a bright future. So thank you.
We have time for a few questions. Yes.
So I have 2 points, one major and one minor, about the cognitive bias, the formalism that you presented. I didn't fully understand how you can actually mathematically, model a cognitive bias like human beings do. Probably I'm not so versed in that, but I would like word how you.
So I can tell you some of what, so we basically are not experts in that. So what we've done is we've followed the literature that's out there. A lot of it is in the behavioral economics type of literature. So for example, there are a sequence of papers on something called the willingness to pay. How much are you willing to pay to take care of pollution, as a society, okay? How much are you willing to pay for this particular car? So we're in a negotiation, and I'm asking you, how much are you willing to pay for this particular car, okay? So we know that, for example, the anchoring bias and other biases will enter into this picture. So we know that if I throw a number at you, I don't know what you have. I wish I knew exactly how much you're willing to pay, because I will then give you a price that's very close to, or the price that you have in mind. And hopefully it's a good price for me, and we're done. It'll be a quick negotiation and we're done. But I don't know that. And you may not even know that, because this changes dynamically as was observed. So what people do is they do a sequence of tests in which they throw a number. So you play a game, and they throw a number, and then you make a decision, and they throw a number and make a decision. They presume a certain model, and they show that the model fits. Okay. For the other type of biases, there are similar experiments that have been performed. They call it in terms of belief update, in which they do similar things. So they will perform a certain number of experiments. They will take data. So this is after the fact, right? And then they try to fit the data to what they've seen, and then they say, okay, the model more or less predicts what we've seen, and so this is a good model. Now, whether it's an exact model or not, probably not. Yeah, we don't know. Probably not, because this. But the point is, I think that the approach, in some sense, is similar to what I said at the very beginning. I really don't care that if it's exact or not. I don't care whether the models for masking, audio masking, or image masking are accurate or not. But to the extent that they're producing results that are meaningful, meaning I can actually compress audio and most of us are happy with that audio, then we're happy. Okay, so there would be the equivalent of this mean opinion score in a sense, which we're trying to come up with other proxies for that.
The other one probably is just a minor slide about the chess game, which is I'm really interested in this, but I couldn't I couldn't believe the result, because if you give me a loan, my particular chess engine, and give me the any group, give me Kasparov, and I will just be a machine and I will beat him. So when you said that, like not really sophisticated like masters in chess, beat like really well-versed masters, this master could use the computer completely and disconnect like a human cognitive, and he will beat anyone. So you blew my mind when you said like, well, those guys win because the interface was much better. And the interface is just a position. Like you give him the position and guarantee.
No, so I don't know what the interface but the interface is actually more than the position. And there are real dollars that are being made based on this observation today. So for example, there is this company, Palantir, that you may have heard of. They are a multi-billion-dollar company at this point. They have a dominant position with the government now in healthcare and banking, etc. And their whole point is that we don't develop machine learning algorithms. That's not our secret sauce. Our secret sauce is that we're doing the machine learning, but we also have this way of helping you to visualize, and we can guarantee you better results. And they're doing great. Okay, they're not the only ones. So another example, which will maybe push it a little bit further. So the group that formed Palantir, part of them came out of, I think it was PayPal. Okay, so within PayPal, what happened is that they had developed some fairly sophisticated machine learning type of algorithms to detect fraud. And these algorithms actually became so good that they could detect, let's say, 80% or thereabouts of all of the fraud. But a lot of the more sophisticated fraud is one that is dynamic. I mean, the person committing the fraud knows how you're going to detect the fraud, and now they're playing games that they're testing new things. The algorithms are not going to work in these situations because they were not trained on this data. They don't, they haven't seen this kind of data. So if you have man in the loop, and then you have machine that is able to cut through the tons of data that's out there, then they were able to detect, many more fraud. Okay, so that's sort of the game, is that you are optimizing the use of the machine where it's great. The visualization is not trivial. I'm not a visualization person, so I don't know how they did it. But there could be an interplay of exactly what you show, how you show it, and when you show it to actually arrive at the combination that does better.
Thank you. Any other questions? Yes?
So let me get this right. Do you build products with your work? Do you contribute to the building of products that solve some of the problems you're facing?
Yeah, so the whole idea, we haven't built anything yet, okay? But the whole idea behind this, so when working, BP also doesn't build these types of products. But they have what they call independent contractors. So for example, we were working with Maersk because Maersk was building their next generation rigs. So the meeting, I mean, you can think of it as a triangle in which we were working with all three of them. At this point in time, we don't have any product that I can point to. But I alluded very briefly on one of my slides on the machine learning algorithms. I said there's the raw data. So there is a suite of programs called the Well Advisor that are specifically designed to deal with specific situations. So if you're drilling, then these are the type of problems you may run into, and this will kick in. If you're removing some of your connections, then these are the type of problems, and that's what will kick in. And so we're sort of entering into this discussion at this point in terms of, how to connect all of these consoles, if you will, because they're all looking at the same data, and a decision that's being made by one might actually affect what's happening in another one. And then the second question is how do you display the information so that it's actually captured by the human being so that they act appropriately.
So we've just come from, Dr. Kerr and I have just come back from DARPA's brain-computer interface group. And it's interesting just to see the teams of people that are coming together to take folks that build algorithms that I'm an industrial designer, so I like to build things, but I'm also a bit of a biologist. So it's interesting to hear you and look at the problem-solving methodology you go through, because I would go at it in a very different way. I may end up in a pocket where I then say I need to get you to look at the algorithm that we would leverage over here, but just I find it interesting to hear your story and then put it in context of what we've just come from at DARPA. It's very interesting.
Sure. I mean, I think again, I mean, in you know, the team that we had, and I should have, you know, we had. I should have shown the slide. I'm sorry. But you know, we had Reed Hasty as a decision person at the business school at the University of Chicago, but he's a psychologist by training. And then some of these guys, all of these guys from BP, yeah, I mean, they approach. I lost the slide. They approach the problem differently from different perspectives. And someone who's not listed, who attended many of our meetings, was actually a fellow who used to work for NASA and then moved to BP on these human factor type of issues. Yeah, so you know, the problem is complex, and you have different people approaching it different ways. But I think when you start talking is when interesting things happen.
Yeah. How do people handle information asymmetry you mentioned?
How do they have that? Okay.
How do people handle that?
I am not sure how you handle this at this point, because today, you know, in my car, when my car says something, I believe it. I don't know exactly to what extent it is working or not working. The same thing happens when you go to the doctors. I mean, it so happens that you know, I went to my doctor not too long ago for my annual checkup, and then he told me, oh, let's do this particular test, which I had read about. And it made no sense because, you know, you look at the false positive that this test is producing, right? So, but if I'm not aware of this, then you do the test, and whatever it says, you believe it. Okay, so there is that problem of we tend to trust others. I mean, it's actually one of our biases, right? We tend to trust others. And we don't know, you know, we don't know what it's based on. And so therefore, when something goes wrong or when it presents something, we don't know how much to trust it. But the other part, which is sort of novel, because if I'm saying I'm going to train on you, you know, that's also extremely difficult because the machine doesn't know you, and it's sort of limited. So there's a lot of asymmetry here in terms of what you really have and what it thinks it understands about you. So I think that this will continue to be a problem. You know, we'll reach some happy medium, maybe, I don't know, but.
Yeah, I was thinking that probably you also mentioned that maybe how to present the information one way or the other way, that might be one possibility also.
Yeah.
But there's also a situation that can be even worse in some sense. If you're under time pressure, for instance, and you are, as you know, as a utilizer of the machine, and you are, you know, engaged as you would like to be, then there might be a situation where there's actually a sort of disagreement between what the machine is telling you and you as a human being. So you get under a lot of pressure because you tend to believe the machine, but at the same time you have this prior that tells you, no, the machine is wrong. Then when you're under, I mean, we feel it. Like, suppose you're driving in New York City and you know that you have to turn right, but your GPS is telling you turn left, and you have like a zillion cars. Basically, you freak out.
It's actually more dangerous because we also are good at rationalizing our decisions. So the machine may be telling us turn left, but I really would like to turn right, and I'll rationalize it. So yeah, I mean.